Let's continue. So now we have an observation that for a direction to be a valid direction to pull out the object, it has to make an angle greater than or equal to 90 degrees to all the mole's inner normal vectors. Okay, so this is what we are going to do now. We see that this making 90 degrees, given a mold face normal vector with these three components. So this is a vector, nx, ny, and z. These are the x, y, z components of a interface of a mold. And this is our direction, x, y, 1. Okay, this is our direction. If they make an angle greater than or equal to 90 degrees, then the dot product of these two vectors have to be less than or equal to 0. Okay, so in other words, this constraint that this direction has to make an angle greater than or equal to 90 degrees with this vector turns out to this: nx times x plus ny times y plus nz is less than or equal to 0. Okay, now for a given mold, for a given top face, for a given mold of an object, what we have is, if the object has n faces, the mold is going to have n minus 1 inner mold faces. One of the faces is going to be the top face. So for these n minus 1 faces, we are going to have n minus 1 equations like this. And the thing is, this nx, ny, and nz values of these mold normals are known. Meaning, if I say given a mold, it means that the mold faces are given. And so these nx, ny, nz normal values, we know for a given mold, we know these values. The only unknowns are these two variables, x and y. Therefore, a mold face is going to give us an equation like this. For example, 3x plus 5y plus 3 is less than or equal to 0. If the mold normals are, for example, 3, 5, 3, if there's a mold normal like this, this is going to give us this inequality. And this equality is a linear constraint. And we see that if you go back to our solution space, where on the z is equal to 1 plane, let's go back to the z is equal to 1 plane, and we have these xy values. Okay, these are our directions. This inequality actually is going to define a line. It defines a line on this plane. So it's going to be, for example, 3x plus 5y plus 3 is a line equation. Okay, this one is going to define a line here, and less than 0, less than or equal to 0 means that it's going to define a half plane. One side of this line is going to be all the xy values that have less than or equal to 0, and the other side is going to be all the xy values that are greater than 0. If you include the points on the line, you have the equality. If you exclude the points on the line, you have an inequality. Okay, so here, if we also have the equal sign, because if it makes exactly 90 degrees, again, we'll be able to slide the face through that mold face. So here, what we have is this constraint given by a face define a half plane on this z is equal to 1 plane. And another face is going to define another half plane. And another face, another half plane. So we are going to have n minus 1 half planes like these. And what we are going to do is, our solution is going to be at the intersection of these half planes. For example, if there's another half plane which says that it is less than here, it's going to be this region. So this part of the first half plane is going to be an invalid equation. So at each step, we are going to be intersecting half planes, and an intermediate intersection is always going to be convex. Okay, if we this is always going to be a convex shape. When we intersect a line with a half plane, we are going to get some, but convex, but possibly unbounded. It may be unbounded, and sometimes the intersection may also be empty set. Okay, or the intersection may be, if this is the valid region for this one, the intersection may be a single point. Sometimes the intersection of these planes may be a single point. Sometimes the intersection may be unbounded or empty set. And these will, all these cases indicate different things. If it's a single point at the end, if the intersection of the n-1 half points is a single point at the end, it means that there is a single unique direction that you need to pull to take this object out of the mold. If it's empty set, it means that there is no way to take the object out of the mold. But then, if there is no way for this mold, maybe you can try another face of the object as the top face. So the thing is, I mean, remember this shape here. We are going to see that the intersection of half planes is an empty set for this mold. But if you take this object upside down, you are going to have a different set of mold faces, and it's going to give you a feasible solution set. So doing this n-minus half plane intersections, we need to do it for all the possible faces, for all the n faces of the object. We are going to try every face as the top face and see whether we have a solution. If in any of those, if at least one of those we have a solution, it means that this object is castable. I mean, there is a way to design a mold for this in which you can cast the object. If none of the faces, in other words, if for all of the faces the intersection set is the empty set, it means that there is no way this object can be pulled out of a mold that is made for this object. So this is the solution we are going to use. Now we reduced our problem to find the intersection of half planes. Okay, so if you can find the intersection of half planes efficiently, you can solve the problem efficiently. Here, in chapter 2, in the previous chapter, we saw the overlay of two subdivisions. Any concave or convex shape. Actually, in this overlay, by using the overlay, we can also compute the intersection of two intermediate shapes. But if we use that solution was n log n, I guess. But I don't remember it correctly. But at the end, it will give you a solution which is n log n. Okay, so it is possible. Yeah, it is possible to find a solution which is going to solve in. Because we can convert it to a problem of polygon intersection. If we intersect polygons at each time, we are going to find it in n log n time, not log n. Okay, this is actually log n is a smaller complexity than n log n. Here I'm talking about n log n times log n, so it's going to be greater than n log n, okay? So, but now the book describes another algorithm, but we didn't make use of the fact that these intersections are always convex. So maybe using the convexity of these regions, we can maybe find the intersection of two convex polygons in a easier amount of time. And the algorithm that the book describes for this is, it's a divide and conquer algorithm. If you have n minus or n half planes, find the intersection of half of them, find the intersection of the other half, and find the intersection of the results. Okay, so it's a recursive algorithm, like merge sort, for example. So it divides the planes into two sets, finds the intersection of the first half, finds the intersection of the second half, and at the end you are going to have two convex areas at the end, and you merge these convex areas by finding the intersection of two convex regions. So this algorithm, if you look at the recurrence relation, so it's going to be something like that. Tn is going to be equal to 2Tn over 2. So I have two recursive calls to half of these half planes. So there are n over 2 of these half planes. I have two recursive calls to that, plus the whatever cost it takes to find the intersection of two convex polygons. Okay. If we use the original algorithm that we use for map overlay problem, this is n log n. The overlay problem was done in n log n time. So if you do not make use of the convexity of the regions, this recurrence relation at the end is going to solve to all n log n log n. Okay, so log square n. But by making use of the convexity of the results, I mean, maybe if the two polygons are convex, finding their intersection may be done maybe easier, okay? The map overlay problem was doing this for any arbitrary polygon. So can we make use of the convexity of these shapes? And when we do that, it becomes, the book gives, again, a plane sweep algorithm which can solve the intersection of two convex polygons in O(n) time. Okay, so if we can do it in O(n) time, then at the end, this one is going to be resolved to O(n) log n in total. So we can reduce all log square n to O(n) log n if we make use of the convexity of these regions. But now I'm not going to talk about the intersection of convex polygons in the book. I mean, we are going to see whether is it even possible to reduce this to O(n). Okay, I'm going to be interested in better solution. Whether is it possible to find our direction, find our feasible direction in O(n) time. And we are going to see, I'm going to now describe an algorithm which actually has a O(n) square worst case complexity. So it is worse than this O(n) log n one. It's not a recursive algorithm. It's an incremental algorithm. We are going to incrementally, we are not going to divide our half planes into two. We are going to incrementally, by adding half plane each time, we are going to compute the feasible regions. But here, in order to have this O(n) time algorithm, I'm going to make this observation. Do I really need to find all the possible directions? I mean, maybe not. If you're only interested in whether it is possible to cast this object or not, all you need to know is that at the end, whether the intersection is a non-empty set or there is some point in the intersection. Okay, this brings our problem to what is called linear programming. In linear programming, usually we are interested in a single solution out of all possible. So this intersection of convex regions, intersection of half planes, at the end is going to give us a convex region, which is an intersection of all the half planes. Okay, this convex region contains infinitely many directions. So any direction from this convex region is a valid direction to pull this thing out. But do we really need to find all of these directions if you're interested in just one direction which is valid? So if you're interested in the whole convex region, there's a proof that you cannot do better than n log n. So you need to use this algorithm if you're interested in the all possible sets of directions, if you're interested in all possible directions to pull this thing out, you are limited with this n log n limit. But in the practical problem that we were asking whether this object is castable or not. So a single direction is a valid solution for me. So if you're interested in a single solution, whether there is a direction, if you ask this, is there a direction that is possible to pull this thing out? So if you're just asking whether the intersection of these half planes is empty or not, then there's an ON expected time solution. And yes? It gives a direction. It gives an extreme point of this intersection. Okay? So it's like this. And now it comes to the, let me talk about linear programming. In linear programming, what we do is that we usually have a set of linear constraints like this, a number of linear constraints in the form like these inequalities. They have to be linear. That hence the name linear programming. But the term programming has nothing to do with real programming. Actually, that term was used before even programs were invented. Okay, so before the word meant real programming, there was this Q term program. It doesn't refer to computer programs. So linear programming does not have anything to do with C programming or other Java programming. Okay, they are unrelated. So it's an optimization problem. So we are given a set of linear constraints like this. And in addition to these linear constraints, we have an objective function, which is also linear in terms of these variables. For example, optimize cxx plus cy y. Okay, so for example, maximize this or minimize this. So we are given an additional linear function. This is called the objective function, which we are required to maximize. You can consider this objective function as a regularization mechanism. If there are multiple solutions, this optimization function gives us a way to choose among these multiple options. So given, if these are all possible solutions, give me the one that maximizes this. And usually this Cx and Cy are given as input, like these Nx, Ny, and Z. We are given a direction in this maximization function. But in our practical problem, what may be, for example, let's try to maybe we may try to minimize this. Minimize x plus y. Okay, it may be from industrial engineering perspective. I mean, it will give you directions that are close to that are close to the center, right? I mean, or is it? I mean, for example, if you want solutions, for example, if there are multiple directions in this funnel, for example, you want to choose the direction that is in the middle. You don't want the angle that it makes with z is equal to 1 plane to be large. For example, if your goal is to minimize the angle between the normal of the z is equal to 1 plane and this direction, you want to minimize the angle between this normal, so this is our normal, okay, of the z is equal to 1 plane, and the directions you found are these, for example. These are valid directions. You want to minimize this angle between the direction you found and I mean between the directions you found and this normal vector. This may be one optimization criteria. Okay, for example, we may want to minimize x plus y. This will give you, out of all possible solutions, it will give you a way to choose a direction. But again, this direction that minimizes this, again, may not be unique. How can it not be unique? For example, both the vectors, for example, 3 and 5, and 5 and 3, both are possible solutions. Imagine both are possible solutions. The objective function turns out to be 8 in both of them. So which one are you going to choose? Again, even in this minimization problem, we may still have multiple solutions. And in that case, you can say, again, you may devise a method to choose between these two, saying that I first order them by their x coordinates and then y coordinates. If you do that, you can again uniquely order these. I mean, if they're equal, choose the one smaller in lexicographic order. If you say that, again, you'll be able to uniquely choose a point. Now, let's get back to this objective function, cx plus x plus cy times y. So cxx plus cyy maximize this function. Now, here, this cx and cy actually is a vector. It defines a direction, again, in our solution space. Based on how we give cx, cy, it defines a direction in solution space. Okay, this is cx, cy, for example. It's a vector in solution space. And maximizing this function with respect to these coordinates is equal to finding an extreme point of the intersection region in this direction. Meaning that, for example, if, let me draw you, if this was my final convex region, okay? This is my final feasible region. If your cx plus cx and cy is a vector like this, it's going to be this point that maximizes this function. So in this region, the point xy that maximizes this function is going to be an extreme point in the direction defined by the vector. Now, when can we have multiple solutions like in this case? If our direction vector is, for example, orthogonal to this edge here, it means that this edge here by itself is extreme in this direction. I mean, this edge, the whole edge is extreme in this direction. And in that case, any point here will be maximizing cx plus cy equally. They are going to have equal objective function value. And in such cases, you can, if you lexicographically order them, you are going to be choosing this point as your objective, as your direction. Okay, so cx and cy will be able to give us a unique solution in this problem. Now, we are going to see that we'll be able to solve this problem. The two variable, this is called, in general, linear programs may contain multiple variables, x, y, z, w, so it may have multiple variables in them. Here, in this specific geometric problem, all our constraints are going to contain two variables, x and y. No other variables are present. As you can see, the unknown that we are trying to find is that direction, x, y. And we impose, therefore, we write the two variable linear program, two variable n-1 constraints linear program. And we are going to show that a two variable one way to do is, there are solvers, commercial solvers, like Cplex or Lingo or Lindo, I don't know. So there are commercial solvers, linear programming solvers. All you need to do is, after you formulate your problem like this, with a set of linear constraints and an objective function, you just give them to those solvers, and the solver is going to tell you, there are algorithms developed, these are optimizers, they are going to give you a result for x and y. And especially if your variables can take any floating point numbers, they can solve this problem efficiently. The difficult thing is, if your variables can only take integer values, this is a special name. This kind of linear programs are called integer programs. Integer programming is an NP-hard problem. So you cannot find, if you're limited with integers, there is no hope that you can find a solution that optimizes this quickly. But if your variables can be floating point numbers, the linear programming solvers can find this efficiently. But today we are going to see if we have two variables, we are going to see that we can solve this linear program in O(n) time. Okay? And being the number of constraints you have. Okay? Yes?
Hocam integer'la float arası zaten yani float'un yani atıyorum float birler için de o zaman yavaş çalışacak. Sadece bir yuvarlamışlar içine. Sevdikten sonra bir tane.
No, I mean, if you give the flexibility to the program that the variables can be floating point numbers, the resulting solution can be integers. They may turn out to be integers. It doesn't mean that the program is going to find it in the computational complexity is not going to increase. But it may give you x and y is equal to 1.5 and 0.8, something like that. But if you impose the constraint that the variables have to be integers, you are not allowed to give them floating point numbers, then you make the problem difficult. It will not be easily, optimizer will not be easily solve this.
Ya integer'la float arası hani düşündüğüm zaman işte 1 ile 2 arası 10 tane daha rakam gelecek. 1.1, 1.2 ya veya 1 ile 2 arası 100 tane de işte 1.11, 1.12 anlatabiliyor muyum? Bu derinlik bir yere kadar.
Yes.
Bunun durduğu bir yer var mı yani bu derinliğin, bu partition'ın?
Oh, okay, I see your problem.
Integer float ne fark eder bir yerde?
Well, that's a good philosophical question actually, but here the problem is, I mean, it's like using floats. In that case, it's like you're increasing your solution space. You're thinking it maybe in a reverse way, but here it's not about the solution space, okay? Our solution space, of course, is not infinite, but giving the problem the flexibility to give a variable the value 1.1, instead of enforcing it can either be 1 or 2, makes the problem difficult. Okay, it's in the reverse way. I mean, it's not the solution space that is considered, because by giving it 1.1 and 2.2, you may be able to maximize this easily. If you're not allowed to give 1.1, 2.2 floating point numbers, then making this integer from 1 to 2, it affects all the other values that you have given. So you need to simultaneously think about all the values you are given to all the variables. This makes it complex. I mean, changing one integer from 1 to 2 may cause all the others to shift to different numbers. Your optimization can change. So that's the main thing that makes the problem difficult. But if you're allowed to do it with 1.1, it may not have a larger effect. So that's the main thing. So programming is more difficult problem. But there's a way which is called relaxation. Even if you have an integer program, you solve it as if it's a regular linear program, and your program comes with some solutions, 1.1, 2.5. Then you round those numbers to the integer values you found, and you may say, okay, this is my solution, but it doesn't guarantee optimality. What you're going to get at the end is going to be an approximate solution. And sometimes even it may not be a valid solution. If you round it, it may not even satisfy the constraints after you round them. So relaxation is used to be able to solve integer programs in short amount of time. But here, right now, we don't have an integer program. We have a regular linear program and two-variable linear program. Our incremental algorithm works like this. We have a certain observation. Okay, this observation is that at an intermediate, so our incremental algorithm is going to use this. We are going to add each half plane one by one and see what this half plane does to our current solution. In order for our solution to work though, we have to, at each point, we assume that we have a unique solution. Either we have no solution or we have a unique solution. Okay? I mean, in this incremental algorithm, at each step, after we add a new half plane, we may either see that the intersection is empty set, or the intersection is going to be a point. Okay, I mean, if we have multiple solutions, this incremental algorithm is not going to work. So, so it's always bounded. We always have a bounded convex region. In order for this to work, we may need to add 2 additional constraints. For example, if we see that initially this is our half plane. Okay, what we do is we add 2 constraints which contain very large numbers. And these large numbers bound these infinite half planes by 2 lines like this, 2 line segments like this. These are added. I mean, these are like you add them, they make it very large numbers so that you bound your unbounded solution space. So if you have an optimization direction like this, even with the first half plane, you are going to have a unique solution, which is this corner here. Okay, so in order, since you have an unbounded, you have infinitely many solutions at this point, you add these imaginary vertical and horizontal lines which contain, for example, you say that y is greater than minus 1 million and x is greater than minus 1 million. Okay, these are my new constraints, which is going to like bound the infinite unbounded solution space with this corner. So if my solution lies to this place, I'm going to see that 1 minus, I mean, this is going to be a possible solution at this point if your optimization direction is this. You can always, so I mean, this is not very critical to understanding the algorithm actually, but here the algorithm, these technical details, these being the intermediate solution being unique, is used by the algorithm because algorithm is based on a lemma which states this. So we have, let me define now some, I'm going to now have some definitions. Okay, and these definitions are going to be used to describe the algorithm. Since we have an incremental algorithm, so let this be the set of our half planes. So our half plane set, okay, let's have them, okay, our half planes, so this is our half plane 1. So imagine we have n half planes that we want to intersect. And here, this is, we also, and imagine the final convex region is the intersection of all these half planes. Okay, the final convex region, this is the final convex region, this is the all set of half planes. The final convex region we are going to find is defined as the intersection of all these half planes. And for each convex region, based on the direction Cx, Cy, we also have and actually this is at the end, and the vertex V is the extreme point of C in direction Cx, Cy. Okay, so we have these 3 things defined. So the intersection of half planes, which is denoted by C, and our whole set of half planes, and the final vertex we want to find, which is the extreme point of this convex region C. Now I'm going to add new variables here, which are, since I have an incremental algorithm, I'm going to find this final H and C incrementally. So at an intermediate step, Hi is going to is going to be the set of half planes up to half plane I, okay, up to half plane I, and Ci is going to be the current convex region that is an intersection of Now let me, for j is equal to 1 to I, hj. Okay, so Ci is going to be the intersection of the half planes up to that point. So if I process them in a certain order, imagine these are given in certain, from 1 to n, my half planes are ordered, and I process the first I of them. After I process the first I of them, I have a certain convex region for first I of them, and these are my first I half planes. And Vi is going to be the extreme point of this convex region. The half planes? Oh yeah, you mean Cx and Cy? It can be any arbitrary direction. It doesn't matter. If your goal is if your optimization goal is not given, like finding a it can be any arbitrary. Cx and Cy can be 1, 1, for example. It doesn't matter. I'm going to give a lemma, and I'm going to stop there. We are going to continue this in the next lecture. So the lemma is this. Okay, this is very important. The whole algorithm is based on this. It says, if now imagine we are going to add a new half plane hi plus 1 to this, okay? If this Vi, okay, is in the feasible set of hi plus 1, if it's included in hi plus 1, Vi plus 1 is also equal to Vi. Okay, I mean, it shows that so actually, if the previous vertex, if the previous extreme point, it's like this. If our previous extreme point is also lying in the feasible region of this half plane, it is still an extreme, it's going to be still an extreme point of the intersection, the whole intersection at Ci. It's going to be an intersection point of Ci. It's going to be an extreme point of Ci as well. The other case is if the previous extreme point is not a member of the new half plane. It doesn't mean that the intersection is empty. It's maybe something like this. So let me draw you this. So I have a current convex region, okay? And if this is the extreme point, the current extreme point, what it tells me is that if the new half plane is here, and this is the new half, if the new half plane is this, the intersection of this with this will not change this extreme point. This extreme point is still the extreme point of the new convex region. If you find the intersection of this with this, again, you are going to, I mean, it contains the whole thing. The intersection is still this region. So this, if this Vi is included in hi plus 1, this will still be the extreme point. If it's not included, imagine hi plus 1 is this, okay? If, in that case, as you can see, our previous extreme point is no longer a valid solution, okay? So it's not Vi plus 1 is not Vi anymore. It's going to be this now, okay? And it tells that this Vi plus 1 has to be on the line that intersects the Ci. So the intersection of Ci and hi plus 1, we find this, and the next extreme point, Vi plus 1, has to be on this line. Okay, so this is, we are going to be using this lemma to find out whether we are going to start with an initial extreme point. Sometimes if the half plane, if this point, extreme point is included in the half plane, our algorithm will not do anything. We are not going to update anything. It's still an extreme point. It's still valid solution. We only need to update our current solution if this is not included in hi plus 1, and if hi plus 1 defines a new extreme point like this vi plus 1, and this is going, we incrementally are going to add these half planes like this, and we are going to update these extreme points whenever needed, and there are only two cases. In one case it's not updated, in the other case it's updated with this intersection of this half point. It has to be on this line, and we are going to see this case, when we need to update this vi plus 1, if it needs to be updated, it's going to take on time to update this, to find this intersection, and where intersection of this with the convex region is going to take on time. So this step is going to be on, and since we may do this update n times when we are adding n half planes, this update may be done n times, so the worst case complexity of the algorithm is going to be O(n) squared. But we are going to later see that the probability that vi plus 1 is not equal to vi that probability is going to be 2 over I. Okay? As we add the new half planes, we are going to see that probability, and this probability is going to be a very low probability. And you see that when the expected running time of the algorithm, so the algorithm has an if statement checking these two conditions. If this is true, don't do anything. If this is true, then do an on time. So if these two conditions, one condition is O1, requires us to do O1 operations. The other condition is ON operation. And we are going to see that we go to ON operation only with very low probability. The expected running time of this algorithm is going to be ON. Because most of the time, the VI, that point is not going to change. The probability that an intersection, an extreme point is outside the half plane is going to be a low probability. Okay, it's the same probability as having out of n lines, so given a point, for example, out of n lines, which two may define this point? Okay, only two of them is going to define this point out of all possible n. So it's going to be, the probability is going to be 2 over n, which is going to be a small probability. I mean, I is going to be at the end n. If there are n half planes, it's going to be n at the end. But it starts with 2 over I. I mean, initially, when I is 2, only there are 2 half planes. It's for sure you're updating VI. But when you're adding new half planes, it's going to be 2 over 3, 2 over 4, 2 over 5. And a new half plane is more likely to contain VI in itself. And this is going to end up having an algorithm with ON complexity. Okay, I'm going to talk about this at the beginning of next lecture in detail. So again, bayramınız kutlu olsun.